Hi all. Now we will discuss about another special type of I/O data transfer technique, which is called interrupt initiated I/O. So the interrupt initiated I/O is a data processing technique, is an I/O data transfer technique. So the interrupt initiated I/O is another type of I/O data transfer technique. So let's see what is the importance of interrupt initiated IO. Before discussing this, already I explained that the programmed IO data transfer, there are certain problems with the programmed IO data transfer technique. One of the major problem with the program is that CPU has to continuously monitor the status of IO devices. So the CPU has to monitor continuously the IO status of the devices. That is one of the major disadvantage of so it is one of the major disadvantage of CPU, that is programmed IO data transfer technique. And because of CPU or processor, CPU means processor, continuously monitoring the IO devices, it is unnecessarily becoming busy, and its cycle time or execution time is getting wasted for unnecessary thing. And this is the one of the biggest disadvantage of programmed IO. And of course the programmer has to take care of everything, right from interrupt, right from IO instruction execution. So instead of continuous monitoring of the CPU, interface will be informed to issue an interrupt request signal. So what happening, let me draw a picture. If this is my processor, which you are also calling as a CPU, which communicates with IO interface and which communicates with actual IO device or peripheral device. So here in programmed IO, the processor has to continuously monitor IO interface when this IO device is ready. Instead of that, we can ask IO device to inform we can ask IO interface to inform the processor when IO device is ready. When it gets ready information and get the data, he can generate and he can send a special signal which is called interrupt. So interrupt is a special kind of signal. So here IO processor, IO interface sends a special signal to processor which is called interrupt. So with this what happens, processor need not to be in the wait state. He can continue with the execution of the remaining instructions other than IO instructions. And meanwhile, when the IO device is ready by sending some ready signal, then this IO interface can send a special type of signal, that is interrupt, to the processor, saying that the pending IO instruction can be executed now. There was some IO instruction which which couldn't be executed due to IO device is not ready. Let's take an example of entering the data by using a keyboard. The user may not enter the keyboard. So till the user enters data, the processor cannot be in the wait state. So what it has to do, the processor can continue execution of the remaining instructions of the same program or same process or some other process or some other program. So by doing which the processor time is not getting wasted, its cycle time is not getting wasted, or its execution time is not getting wasted. And meanwhile it can meanwhile when the user enters the data using keyboard, that means when the device is ready, the processor, when the device is ready, the IO device sends a signal to the IO interface, and this IO interface sends a special signal to the processor, which is called interrupt. So this type of data transfer technique is called IO, or interrupt initiated IO data transfer technique. So here what's happening, let's discuss in detail about what's an interrupt. So the drawback of the programmed IO is that busy wait loop of the CPU. So let me discuss the 3 points. Meanwhile, the CPU proceeds to execute another program. When there is an IO instruction which is pending to be executed, uh, the processor can take other instruction. Meanwhile, CPU proceeds to execute another program or another instruction related to same process or different process, and interface keeps monitoring the device. So now the job of monitoring the input devices is handed over to IO interface. In programmed IO, the CPU or processor uh, is in the wait status by continuously monitoring the status of the IO devices. So instead of that, in interrupt initiated IO, what's happening? This job of monitoring the concerned IO devices uh, is handed over to IO interface. When device is ready, when device is ready for data transfer, it generates interrupt request. That means IO interface, it informs the IO interface, and IO interrupts generates an interrupt request. So the who generates interrupt request means it is the IO interface which generates an interrupt request. Here the CPU stops task it is performing upon receiving the interrupt. When an interrupt is received sent to CPU or processor might be executing some instruction, so it has to complete that instruction execution, the current instruction execution, and stop executing the remaining instruction. That is, the CPU stops the task it is performing, process the data transfer, then resume the original task. Now let us discuss in detail about interrupts. So the drawback of the programmed IO data transfer technique is that we are keeping unnecessarily busy wait loop. Who processor is in busy wait loop. So due to the time needed to poll if IO device is ready, the processor cannot often perform useful computation. So instead of using the busy wait loop, let IO device alert the processor when it is ready. So the hardware sends an interrupt request signal. This is important. So the signal that is sent by the IO interface to the processor is called interrupt request signal. Interrupt request signal. So instead of using a busy wait loop, let IO device alert the processor when it is ready. The hardware sends an interrupt request signal to the processor at appropriate time, much like a phone call. So you can resemble with a simple example. Meanwhile, the processor performs useful tasks. So let's look at some simple example for understanding the concept of interrupt. Consider a task with extensive computation and periodic display of current result. The timer circuit can be used for desired interval with interrupt request signal to processor. So the two software routines, compute and display. Let's assume there are two software routines, the compute and display. Processor suspends compute execution to execute display on interrupt, then returns. The display is short, time is mostly compute. So we'll try to understand this. There are two routines called compute and display. So display is related to output device which displays some content, and compute is just executes or performs some uh, computation. And when compute performs the computation, it has to wait before performing the next computation, so that display displays whatever the computation it has performed. So consider a task with extensive computation and periodic display of current result. So it's not like compute performs a computation of something, some x, and display that x. Once the display of x is completed, it should send some signal, then it performs the computation of y, then y should be displayed. So it is just like, let's assume two routines, computational and display. Computation computes x, sends to x, sends display x, sends some signal, then computation performs another y, sends to y, display this y, send that x is completed, display y is completed. This is called interrupt. Or let me give you a brief idea. Let's assume there is one person who is a manager, assign some task to his office subordinate, and let's assume this task may take some 20 hours of time. So this manager, he can, how it would be, after assigning the job, the manager, if continuously asked for every 1 hour and he is in a wait status, then it is a unnecessary headache for the manager. He cannot do any other task other than just monitoring whether this office subordinate is doing the task or not. Instead of that, once the manager after assigning a task, he can continue with his other related work. When this work is completed by this office subordinate, he himself makes a call. This call is nothing but interrupt. So we'll see some now. We got some idea about interrupt. We see the similarly, if you resemble the manager with processor, here processor is the manager and the IO interface is the office subordinate. Once he assigns the job, a particular job, what is the job here? IO operation. This is important. Any IO operation, input or output operation. Example for input and output operation means if the user requires to enter some data using a keyboard, it's an input operation. Likewise, if some value has to be displayed on the monitor, then it is an output operation. So this processor, the execution of this IO instruction by the processor depends upon involves IO devices. So this cannot be, we cannot say that the IO execution can be completed only a certain time limit. It can take so much of time. So the processor cannot be in the wait state. After assigning the job, it depends upon the ultimately whether IO device is actually ready or not. Once the IO device is ready and sends the data, everything is ready with the IO interface. The IO interface makes a call or office subordinate means the IO interface makes a call to the manager or processor. This call is called interrupt, as simple as that. Now we see the technical how we got to know that interrupt is a special signal that is generated by the IO interfaces, that is interrupt request signal. You should remember these terms. The interrupt request signal, it will be sent to the processor. So so the interrupt service routine, there is another word called interrupt service routine. So you see, the interrupt service routine, there is a special term, but you should understand that the processor is getting interrupt request from IO devices. So when the processor receives interrupt request signal, what actually happens? Let's look at the previous example. That is, we said that display compute is one routine and display is another routine which sends interrupt signal, something like that. So display is an interrupt service routine, differs from, there is a special word called interrupt service routine. What is interrupt service routine means? Let me give you a picture. As of now, we know that processor receives interrupt request from IO interface. Upon receiving interrupt request from IO interfaces, what processor has to do? Processor has to complete the current instruction execution. Remember this point, it's very important. It has to complete the current instruction execution because it might be in the middle of uh, instruction execution. And you know, instruction execution, there are four steps: fetch, decode, execute and store. So the processor might be in the middle of doing fetching operation or decoding operation or the executing operation or store operation. It has to be completed. So it will complete, if it is in the fetch state, it will complete the decode, execute and store. So it completes the current instruction execution. Then it will look at the interrupt, what kind of interrupt it is, who generated interrupt. According to that, it executes a special routine called interrupt service routine. So the interrupt service routine means the processor already will give some interrupt service routines to the processor. Let's assume there are two types of interrupt request: interrupt request 1, interrupt request 2. If the interrupt request 1 comes to processor, service routine 1 should be executed. Similarly, service routine 2 be executed for interrupt request 2. So it is one kind of handling the interrupts. The handling of the interrupt is done by executing a concerned interrupt service routine. So what I'm trying to say, for interrupt 1, interrupt request 1, the processor has to execute one subroutine, interrupt service routine 1, ISR. If the IO interface generates another interrupt called interrupt request 2, then this processor has to execute another type of routine called interrupt service routine 2. So this interrupt service routine is specific to the type of interrupt. Just for example, I am taking 2 interrupt requests, but there will be more number of interrupt requests. So for each interrupt request, there is an associated interrupt service routine. So this interrupt service routine differs from the normal subroutine because it is executed at any time due to interrupt, not due to call. Interrupt service routine is just like a normal routine, subroutine, but the only difference is the interrupt service routine is executed when concerned interrupt request is generated. For example, assume interrupt signal asserted when processor is executing an instruction I. Let's assume there is a processor is currently executing the instruction I, and meanwhile interrupt signal is generated. So the instruction completes, the processor has to complete the current instruction execution. Then the most, and it has to do certain things which are very important. The first point is that PC should be saved to temporary location before executing interrupt service routine. It's the most important thing. See, when the processor or CPU, we are learning step by step. First, we understand that IO interface generates an interrupt request signal, and upon receiving interrupt request signal, what processor has to do? Processor has to complete the current instruction execution, and it has to execute interrupt service routine related to this one. If this is interrupt request 1, then particular interrupt service routine 1 has to execute. But before doing that, what it has to do? Copy the content of PC to somewhere, some temporary location. Why it is important? See what PC contains. PC is a special kind of register which is called program counter, which holds the address of next instruction to be executed. We see while when interrupt request is sent to processor was not idle. It was executing some instructions. Let's assume it was executing some instructions of a process, and it is completed 3 instructions, and it is currently and executing the 4th instruction, and there are 5 more instructions to be executed. This is the scenario. Then what PC contains, since processor is currently executing 4th instruction, the PC contains the address of the 5th instruction. So when this processor receives the interrupt, what it has to do, just it has to execute interrupt service routine, and it has to come back to execute the 5th instruction. So the already 4 instructions were executed by the processor. Only it has to execute the remaining 5 instructions, and it has to execute the instruction. It has to resume the instruction execution from 5th onwards. So it is important to keep track which instruction has to be executed next, and that address is present in the program counter. So it's very important that processor, before executing, upon receiving interrupt request signal, Before executing concerned interrupt service routine, it has to do certain things, and one of the most important thing, and the first thing is that load the content of PC to some temporary location. So this 5 is stored somewhere else so that when it comes back it can continue the instruction execution. So this is the most important thing. So the PC is saved to temporary location before executing interrupt service routine. And return from interrupt instruction and this interrupt service routine, we are talking about interrupt service routine, and return, the last statement is return from this interrupt service routine, and this will restore to some PC address with the instruction I plus 1. So the processor was currently executing ith instruction, here I was 4. When it is executing fourth instruction, the value of PC is fifth instruction, that is I plus 1. So store this I plus 1 in a temporary location. Next we see issues of handling, issues for handling interrupts. So save the return address on the stack or in a register. That means that whatever temporary location we are calling, the content of the PC, I said, has to be transferred to some temporary, that is nothing but it can be a stack or it can be any other register. So the return address is the address that is stored on the PC, is nothing but return address, and this can be stored on a stack. And you know the stack, right? Stack follows the principle of last in first out, or this the address of next instruction, that is the PC value, can be stored in a special register. So interrupt acknowledge signal from the processor tells the device that interrupt has been recognized. Now we see the sequence of steps. When processor is executing fourth instruction and the content of the PC is 5, it receives interrupt request signal from an IO interface. Upon receiving this, it has to execute interrupt service routine 1. First step is it receives interrupt request signal. When the processor completes the current instruction execution, the processor completes current instruction execution, then copy the content of PC to some stack. First is receive interrupt request signal. Processor has to complete, second step is processor has to complete the current instruction execution. Third step is load the content. Third step, what is actually, this is a fourth step. The third step is send an interrupt acknowledgement signal. This is third step. So the processor says that yes, I received the interrupt, let me give some time to process it. So this is called interrupt acknowledge. So upon receiving the interrupt request, immediately processor will not set interrupt acknowledgement. Complete the current instruction execution, then send interrupt acknowledgement signal from processor tells the device that interrupt has been recognized. In response, the device removes the interrupt request, saving or so what happens, the device or IO interface removes the interrupt request, Saving or restoring general purpose registers can be automatic or program control. Now the fourth step is load the content of PC to some stack and copy all the register values to some temporary buffer or location, and go to the interrupt service routine 1. But the important question is where this interrupt service routine 1 is stored, whether it's in the memory. Ultimately it has to be in the memory. Now you understand that the main memory, if it's a 4 GB location, then certain memory is reserved by operating system for doing all these such things. This is called system memory, which is called. So the processor sends interrupt acknowledgement signal to the concerned IO device, IO interface, and copies the content of program counter to some temporary location. It is called stack. It can copy to stack or any other memory location or register. Now the question is, where is this interrupt service routine? That is, we are saying ISR, right? ISR, that is interrupt service routine, where it is saved. It is the one of the most important thing. Now you should understand that the memory, or you can call the main memory, is divided into some parts which is called system memory, and this system memory is stored for all interrupt service routine 1, routine 2, etc. So when the there is some table kind of thing where if the particular interrupt, if the processor receives interrupt request 1, then interrupt service routine has to be executed, and this is its address. So the processor has to look this table. This table is also stored in the main memory. Now we see enabling and disabling interrupts. The processor must always respond immediately to the interrupt request from IO devices. Some tasks cannot tolerate interrupt latency and must be completed without interruption. Need ways to enable and disable interrupts to provide flexibility to the programmer. So what happens? There should be a provision to enable or disable interrupt. So there should be a provision to enable or disable interrupt by for whom? The programmer. Then the user control bits in the processor and IO registers. So there should be some flexibility given to the programmer to enable and disable interrupt. It is very important. Now we see some sequence of events when an interrupt is generated. We see some sequence of interrupts. First, what happens? The processor status register has interrupt enable bit. So the processor has one special register which is called status register, which has interrupt enable bit, that is called IE, interrupt enable bit. Program sets interrupt enable. Now there is a provision that the programmer using the program can set interrupt enable bit to 1 to enable interrupts. So this is most important thing. The processor has to understand that the it cannot service the request if the interrupt is disabled, if the disable. So the interrupt can be enabled or disabled, and this provision is enabling disabling provision we are giving to the programmer. If the programmer sets interrupt enable bit 1, then interrupt is enabled. The processor can receive interrupt. When an interrupt is recognized, when an interrupt is recognized, processor saves the program counter and status register. We know this process. So first, let us look at the sequence of events that occurs during an interrupt. First, the processor status register. The processor maintains status register. Processor maintains a status register, and this status register is has one bit, special bit, which is called interrupt enabled bit. So the programmer can enable or disable an interrupt. So it is in the hands of the processor, programmer. He can enable or disable an interrupt simply by setting the interrupt enable. There is a special bit in processor status register, which is called PSR, the processor status register, and it can be set to 1. Interrupt enable can be set to 1. When an interrupt is recognized, the processor saves the program counter and status register. So the first step, the moment interrupt request goes to processor by IO interface. What is the first step means? The moment interrupt register receives the moment the processor receives the interrupt request, it completes the execution of the current instruction. Remember, the instruction execution phase, it may be fetch, decode, execute, and store. So these are the instruction execution stages: fetch, decode, execute, and store. So the current instruction might be any one of these phases, and during this phase it cannot stop the execution, so it has all the 4 stages of the execution has to be completed. So once the processor receives the interrupt request, and it might be executing the instruction execution at any one of these 4 phases, it will complete the instruction of the execution of the current instruction, and then it saves, and it will send interrupt acknowledgement signal to the. So the first step is receive interrupt request, complete current instruction execution. Third, send interrupt acknowledgement, and then fourth step is to save program counter and status register. Save the program content counter to stack, and there are some status registers. Interrupt enable bit. Interrupt enable bit is cleared to 0 so that same or other signal doesn't cause further interruptions. Next, the IE can be bit cleared to 0 so that the same, so when you are processing one interrupt request, another interrupt should not occur. So for that, what happens, you will set interrupt enable to 0. After acknowledging and servicing interrupt, restore the saved state and set interrupt enable to 1. This is about event sequence. Next, handling multiple events. Handling multiple devices. So handling multiple devices means which device is requesting the service, how is appropriate service routine is executed, should interrupt nesting be permitted. So for first question, which device is requesting the service, poll device status registers, checking if interrupt IRQ, interrupt request for each device is set. Second one, how appropriate service routine is call device specific routine for first set IRQ bit, that is encounter. Now let us look at first issue read command to IO module. Read the status of IO module. Check the status. If it is ready, read word from IO module and write word into memory. If it is done, okay. Then if it is not, repeat the same process. So issue read command to IO module means CPU sends an command to IO module, IO interface. Then read status of IO module. Then interrupt IO interface sends a request to CPU. Next comes check the status, verify the error condition. If it is ready, then read the word from IO module. So the IO interface will send the word to CPU. Write the word into memory. CPU means processor writes the data into memory. If it is done, okay. If it is not done, repeat the same process. So there are different kinds of interrupts exist, and example for such interrupt is that there are various sources of interrupts. This could be both internal or external. So interrupt can be an internal interrupt, or it can be an external interrupt. So these could be both internal or external. And example program interrupts. The first one is program interrupt. They are generated by some condition that occurs as a result of instruction execution. So your program itself can generate an interrupt. Your program itself can generate interrupt. It is called program interrupt. They are generated by some condition that occurs as a result of instruction execution. Second one, timer interrupts. So these timer interrupts, they are generated within the processor and allow OS to perform certain operations on regular basis. So this timer interrupts is especially used by operating system to manage the internal tasks, such as the best example is garbage collection. Or it is a response after the completion of program execution. In case of object-oriented programming languages or some other languages, what happens? It is important to know, it is important to collect unused memory, and it is called garbage collection. Next, IO interrupts. These are very important interrupts. So the interrupts are of different kinds. One is a programmer interrupt, and the other one is timer interrupt, and the third one is IO interrupts. They are generated for initiation or completion of IO operation. So IO interrupts are generated for initiation or completion of an IO operation. By this time you should clearly understand what is meant by IO operation. It can be input operation or output operation. Next we have hardware failure interrupts. See, the hardware failure interrupts are very important interrupts. They are generated by failures such as power failure or memory parity error. Remember, even on power failure, an interrupt is generated. Even on power failure, an interrupt is generated. So these are the various kinds of interrupts that can occur in a system. Let me repeat, they are program interrupts, timer interrupts, and IO interrupts, and hardware failure interrupts. So these are the about interrupt initiated IO. Let me explain. Remember, the processor has to continuously monitor IO interface in case of programmed IO. So to overcome this, we have a concept called interrupt, and the English dictionary meaning of interrupt is some kind of disturbance. The meaning of interrupt is nothing but some kind of disturbance. Who is creating disturbance? IO interface is creating disturbance to processor. But here the question is, what if more than one IO device generates an interrupt, want to generate an interrupt? See, this is my IO interface, and these are all IO devices. IO devices 1, 2, 3, 4, 5, 6. Only one interrupt. The processor can process only one interrupt. But what if all the devices wants to generate an interrupt? Then there comes a concept called polling. And if the biggest disadvantage of IO interrupt is that if large amount of data has to be transferred from IO device to memory via processor and IO interface, then it is required to generate more number of interrupts. The more number of interrupts are not suggestible, because each time you generate an interrupt, the processor has to keep aside what it is doing, and it has to execute interrupt service routine. So with this, what happens? The normal job of the processor gets disturbed. If it is small amount of data to be transferred from IO devices to memory, then interrupt works fine. But if you have the large amount of or bulk amount of data to be transferred, then it is not suggestible. IO interrupt, even in fact, it is a kind of overburden to the processor. So the solution is, if I want to huge amount of data or bulk amount of data to be transferred, bulk data to be transferred from IO device to processor, the solution is DMA. DMA stands for Direct Memory Access, DMA, which we will discuss in our next class.